So today we will see some properties of, actually we are interested in this because we are in the course we are going to pump in signals through systems. For simplicity we will consider linear systems. So, and we will get some signals out, and we will be talking about the properties of these signals that are going in and the signals that are going out. So we need to know that if a random process excites a linear system and produces an output, then what are the properties of the output vis-a-vis the properties of the input, right? So that is a very important thing for us. So we are going to take a first look at that. Before that, remember that we had in the last class we had talked about we defined a random process, discussed we had defined random processes, defined two random processes, defined their cross correlations, and finally we talked about stationarity, because we said that we want to we don't want the, as such the problem is complex enough, and if we have the the statistical properties varying with time, then we have a huge problem at hand. So sometimes we will just to simplify the problem, and so that at least in there are, if it so happens that the stationarity assumption cannot be satisfied, then we have to deal with such a complex problem. But there may be various situations where the stationarity assumption is satisfied. So it is better to see that under that assumption what results we can obtain, right? It's very important to obtain results, otherwise we get nowhere. So we said that so we defined stationarity, saying that the probability distribution function becomes invariant to a shift in the time axis. So if you have fx t plus c, it is equal to fx t for all c, right? and this happens for an arbitrary degree of joint probability distributions. That is, you take any one, you take two of them, you take three of them, and you take t1, t2, t3 up to tn times, and then you shift each of these times by c, it will remain invariant. So then we don't need to bother too much about the time shifts. That is the advantage. And now it is very difficult for processes to satisfy this definition, because of the fact that you have to consider nth degree joint distributions. So that is even not only that it is difficult to satisfy, it is even difficult to check. You can't say whether something is really strict and stationary. It's very difficult to check. So people thought that, okay, can I do with only 2 degrees? So came the concept of wide sense stationary processes, where the mean is a constant, and the covariance, which will involve only 2 degrees of joint distribution, will only depend on the time difference between the first time argument t1 and the second time argument t2. It will only depend on the time difference, not the absolute time. So if one thing is t1 plus 10, another is t2 plus 10, it will still be same, and this will hold only up to the second degree. Here I was telling that it will hold for all n. So now I don't want that it be holding for all n. I just want that it be holding for n equal to up to n is equal to 2. Okay. So if it holds that way, then I say that it is a wide sense stationary process. So and then we had shown that if something is strict sense stationary, then naturally it is wide sense stationary. That is a fairly obvious result. But now we are talking of random processes and talking of functions of not only functions. Actually, we are going to talk of operators of random process. What is the difference between a function and an operator? Generally a function is a memoryless operator. That is, if you give x, you get y. But if you have an operator, then if you just give x, you don't get y. To get y, you need many x's, right? So it depends on, let us say, if it's a causal operator, then it will depend on all past values of x. Only if you are given all past values of x, you can determine the output y. Just given one value of x, you cannot determine the value of y, right? As happens in any system which stores energy or is or is supposed to have memory, right? So now we are going to talk about such operators, but that immediately makes the case much more complex. So we will restrict ourselves to linear operators. So just once going back to our old definition, that is, how do we finally we should be able to relate everything from our probability space, that is from the experiments. So if we can find that given x t is I is a random process, so corresponding to every experiment xi, every experimental outcome, you have a function xt. Now if you take an operator, if you apply an operator t on that function, and then you get another function yt, then you can say that now you can directly associate this function with this xi. So now again you can that is for each y you can associate it with an outcome, so it becomes a random process itself. So we say that yt is a random process, and we briefly say that yt is, this t stands for an operator, so yt is the output when you operate it with t on xt, right? So it is in this sense, that is, remember that the sense is that you are doing an experiment, corresponding to every outcome you are getting a function, on that function you are passing through the operator and you are getting another function, and that function is that function you are finally relating to the outcome. So that way it is going to be related to the probability space, right? It is also a random process, right? So, and remember that this function itself is deterministic, that is its argument is random, but the function is not random. Once you get an argument, you are applying a deterministic function. Now, it's not that for one outcome you are going to feed it through a low pass filter, for another outcome you are going to feed it through a high pass filter. Such a situation does not occur. You have a single low pass filter, let us say, and every time you are getting a random signal xt, you are feeding that to the same low pass filter t, and you are getting an output. So t is deterministic, but its argument or its input is stochastic, right?
So t is the operator.
T is the operator. So in this case, whatever is the linear system operator, it could be a convolution operator with the impulse response. Normally we get the output y. I mean, I cannot cover these things. Perhaps it is also known that if you have a linear system, then the corresponding operator is a convolution operator with the impulse response. So if you convolve an input with the impulse response operator, then you get the output, right? So this is the sense, and we will mainly generally assume linear dynamic operator. See, the case of static operators or memoryless systems, which are just functions, is actually very simple. We have already derived cases of how a random variable gets transformed to a function. So now if you apply a memoryless function, then you are simply taking each value of t, taking the value of xt, passing it through the function. So it is nothing but a sequence. I mean, it is nothing but transforming a random variable from time to time. I mean, instant by instant. So there is no additional complexity in that. So memoryless operators are exactly to be treated in the same way as you treat a function of a random variable. I mean, simply for every argument t, treat it as a random variable, because we know that if you freeze t, then a random process becomes a random variable. So simply apply it to a function. We know how to apply functions on random variables, and you get the corresponding value of the process y at that point of t, and then you do it for all t. There is no complexity. The whole complexity arises for memory systems with memory, because now yt does not only depend on xt, it depends on, and in general it depends on an infinite number of past values. If we talk about causal operators, in the physical world most operators are causal, but that does not mean that in the signal processing world all operators are causal. I mean, especially in image processing, or even in problems such as smoothing, we will see, I mean, we regularly apply operators which are non-causal. So in any case, causal or non-causal, they will depend on a number of values of x. That's what brings the additional degree of complexity here. Okay, and it is also reasonably easy to prove that if xt is strict and stationary, then yt is also strict and stationary. That is very simple to prove just from this integral, because this remains shift invariant. This in any case does not contain t, so this will also remain shift invariant. That is very simple to prove, provided g is a function of x only. So now we come to linear systems. Okay, so we talk about yt is a now it's a linear operator of xt. By what do we mean by a linear operator? That is, if you take an x1 and you get a response y1, and you get a, if you take x2 and you get a response y2, then a1x1 plus a2x2 will produce a response a1y1 plus a2y2. Standard superposition is the that is what is, I mean, defines a linear operator. And we are also going to talk about, we are treating a simple case, because otherwise the complexity will sort of blow up on our face. So we are thinking of a linear time invariant system. So which means that the characteristic, that is, let us say the gain of the system that we are talking of, that does not change with time. So if you apply a signal now and you get a response now, you will get the same response if you apply the input 2 seconds later, and you will get the same response 2 seconds later. So the gain does not change with time. So the system characteristic does not change with time, right? So we will generally be talking about linear time invariant operators. Now this is a very interesting result, first important result, which shows the linearity of the expectation operator. That is, if you take the expectation of the output y, it is just like feeding the expectation of x, passing it through the filter. So if you know the expectation of the input, you can directly calculate the expectation of the output without actually feeding each one of them and then calculating expectation. That is, you don't have to calculate actually perform how many y's you got in that range and all that. You actually don't have to do it. If you know the properties of x, just by feeding it to a linear operator directly, you can get the expectation of y. That is a very significant result. Okay, I mean, these things really, I mean, this is why, I mean, linear is so beautiful and convenient, and we spend so much time on linear, because if we did not have these simplicities, I mean, it's very difficult to move ahead. Similarly, in many cases, sometimes in this course we will try to restrict ourselves to discrete time systems, because of the fact that, strictly speaking, continuous time systems pose some very tricky mathematical problems, like I mean, how do you define the derivative of a random process? Okay, these things become tricky, and I mean, you can have volumes. In fact, there are 2-3 different kinds of stochastic integrals. I mean, very basic operators like integrals, differentials. You have to evolve their own definitions. I mean, they have to be defined mathematically in some very complicated senses, strictly speaking. While if you deal with discrete operators, then you are only dealing with additions and, I mean, addition, subtraction, multiplication. So you can handle things with very simple operators. So that sometimes, I mean, reduces complexity. So we will often talk about, I mean, present results with discrete time systems. So in the discrete time sense, expectation of yn is equal to what? I mean, this is a kind of proof of this in the discrete time case. So what is expectation of yn? Yn is given by this impulse response operator, because we are talking about linear systems. So it is h of nk of xk. If you had linear time invariant system, then this h of nk will be equal to h of n minus k. There will be only one argument. So now what you have to do is, you have to take the expectation inside, right? Linearity. So you can take the expectation inside, and this is a constant quantity because our system is deterministic. So there is nothing probabilistic about our impulse response. That is a fixed function. So we take it inside the summation, and then it becomes this. This is a very simple proof. There are again subtle mathematical complexities, especially when the system is unstable, because if the system is unstable, some of these limits may not exist, you know, this sum will not exist and things like that. Suppose you have an integrator, then you suppose this xk has a non-zero mean, and this system, this hnk stands for an unstable system, let us say an integrator. So what you are going to do is you are going to sum this xk every time. Now xk is non-zero and you are summing it over an infinite number of terms, so it will, so that limit will not exist at all, right. So such complexities may exist, but for the time being we'll keep our eyes shut on that and only talk about, you know, Bibo stable inputs for which this I mean actually the impulse response sequence will be I mean convergent, that is a result for which this sum will actually converge. So we will only talk about those systems for the time being. I mean I am just mentioning that there are some pitfalls, mathematically speaking, which you might encounter in the textbooks, but I am for the time being not discussing them, because then you will go to the depths of maths. Okay, if you are interested you can always read it, it's very interesting. So it turns out that expectation of yn will be nothing but this for LTI systems, and now this is sometimes written as, you know, if you are familiar with Z transfer functions, then you can easily recognize that if you get the Z transfer function and if you put Z is equal to 1 there, then you get what is this. In fact, it is the steady state gain of the operator, right. So if you are given a transfer function of a filter, let us say, then, and if you feed, let us say, a random sequence which has a mean of, let us say, 1, and if you are given that filter, then you can, using this formula, you can at one shot you can determine what is going to be the expected value of the output, right. So that is simple. Remember one thing, that does not mean that we are going to feed a DC to that filter, right. If you fed an actual DC to that filter, you would have also got that output, but here we are not feeding a DC, we are feeding a signal whose mean value is something. Signal is still AC, and AC means varying, right. So don't make that mistake that we are going to feed a constant DC signal. We are not going to feed that. We are feeding a random process only with a non-zero mean, and then we are trying to get the mean of the output. So output is also going to be a varying process. So having talked about means, we need to talk about covariances. This is perhaps a bit frightening. Nothing. I mean, this is, you know, if you really go continuous, and let's not. Probably I'll skip this transparency if it's so intimidating. So let us come to a simpler case of discrete time wide sense stationary process. So what is happening? This is familiar. This is the standard impulse response. I mean convolution response. So now if you want to calculate what is the cross correlation function, that is equal to nothing but expectation of xm and to yn. Another thing I would like to mention, that in many books you will find that these random processes are often assumed to be complex quantities. So a complex quantity is nothing but, I mean it is something like a two-dimensional vector, you know. I mean you simultaneously deal with two different random processes. One is its real component, another is imaginary component, and you keep on dealing with them together. This is often done especially for communication systems, but that again will bring in more complexity. So what I have decided is that in our course we will, unless we come across a situation where it is really needed, we will always talk about real variables. So all variables are real, nothing is complex. Okay, in the book you will find things which are complex. So all you have to do, everything is similar, is that if anywhere you find a complex conjugate defined on a time function, simply ignore that complex conjugate, because for real variables complex conjugate is the same as itself. So wherever you find h star t, simply call it ht. Okay, that will give you the corresponding results for real variables. We are considering real variables here just to reduce complexity. So that's why if you see complex, you will find that Rxy Mn is actually defined as xm y star n. That is the definition of the cross correlation function for complex processes x and y. But since we are considering real processes, so it is xm into yn. Y star n is equal to yn. Okay, so we need to remember that. And obviously, if it turns out again, this is a very well developed subject mathematically. So I have written this. So it is very legitimate to ask that how do you know that if I mean x is White-Sense stationary, how do you know that x and y are going to be jointly White-Sense stationary? That has not yet been proved. But the fact is that it can be proved. So we will not go into those things, and let us, because otherwise we will not be able to see any result. So it turns out that if x is jointly stationary and we have a linear system, then x and y are going to be jointly White-Sense stationary, which means that their cross correlation can be defined as m minus n. This is a result. Okay. So now let us come to this. Once we know this, so it is nothing but what is going to be Rxy? It is h of n minus k into Rxx m minus k. This how to obtain this? This is reasonably simple to obtain. Only thing is that in place of y, that is actually in place of y, that is what you have to do is what you have to do is just for this yn you substitute this expression, then you will get this, and then you put the expectation inside, right. So you will get expectation of xm into this. People are feeling sleepy. So you put xm into, in place of yn you can put this, and then you can bring the expectation inside. That is a reasonably simple thing if you try. So it turns out that this is going to be your Rxy, and if you just play with the indices, like for example if you define L is equal to k minus n, then you will find that just by switching indexes from here you can kind of, what, suppose L is equal to k minus n, then here you have h of minus L, here you have m minus L, m minus n minus L. Why am I doing it? I am doing it because I want to get it into a beautiful form which you will remember easily. Okay. So now what is this? This itself is a convolution integral, if you realize. So it turns out, so this is the beautiful result, that if by convolving x you get y, then by convolving Rxx you get Rxy. So even the same convolution properties hold even on the autocorrelation function. That is what is the beautiful result. Okay. And now here, why this minus m? Here there is no minus m. This minus m because I have transformed the second quantity. If I would have transformed Ryx, I would have got hm here. Okay. Now finally we are interested in Ryy, that is what is the property of the output with respect to itself, that is autocorrelation properties of the output. Then this will be, now you see that if we, as I said, that if you transform the second argument, then you get minus m. If you transform the first argument, you get this. That is also an exactly similar result. So if you have Ryy, then you can take Rxy and then you will get hm star. So finally Ryy can be expressed as this. So you see that the autocorrelation function of the output you have obtained given the autocorrelation function of the input and the system properties. This is the importance of the result. Without these results without these results it is nearly impossible to find out, I mean, probabilistic properties of the output. Why? Simply because of the fact that, I mean, this is what is the complexity. This is why these results are so crucial, because just imagine that if you really wanted to go from basic principles and tried to find out exact probabilistic descriptions of y, then for each y is now a function of an infinite number of x. So if you really want to find out the probability density function of y, then you have to consider an infinite order joint probability distribution of x just for one value of y, because it is a function of an infinite number of points of x. So that way if you go, I mean, you are nowhere, right? So that is why essentially we have to restrict ourselves to first and second order properties, and we'll have to use these results. See, this result does not at all go through that path, right? That is why it's so useful, and these results will be used very much. It turns out that these are very interesting to prove. You can really try to prove some of these. That is, the autocorrelation function of with any value of m is going to be less than or equal to the autocorrelation function at 0. This is very interesting to prove, and it's very easy to prove actually if you realize that for this must be positive. This has to be greater than 0 because each term is positive and all probability density functions are positive. So if you take an expectation of an all positive quantity, then its expectation must be positive, right? So if given this, to prove this is simple, just open the bracket, okay. In fact, you don't need to put a magnitude, you can just put simple square. Similarly, you can prove that the correlation coefficient is always less than 1. You can also show that it is a symmetric function, Rxx m is equal to Rxx minus m, and this is a property which is known as the positive definiteness property of Rxx. Actually, if you put it in matrix form, it becomes simpler to understand. In the scalar form, this is the relationship. It says that if you choose any number of constants and then construct this function, it will always be greater than 0. That is the for all correlation functions. In fact, I mean, unless these properties are satisfied, a function cannot be called a correlation function. These are some well-known properties. Now, you see, remember that linear systems, we are always talking in terms of frequencies. Hardly we really talk about time. Why? Because of the fact that our algebra becomes so simple. One of the abiding reasons. Because every time, I mean, evaluating a convolution integral is not a joke. So it turns out that if you, I mean, Fourier transform has such a nice property, that is, I mean, that's why out of all the transforms, this transform is so popular, is because for linear operators, the convolution integral becomes a multiplication. So everything is simplified. You say YS equal to GS into US, right? I mean, that is so convenient. I mean, you just simply multiply, right? Calculus becomes algebra. So I mean, that is why we are so obsessed with Fourier transforms and Laplace transforms. So it will be of natural interest to know that can we define these time domain properties that we are deciding, these means and these, I mean, autocorrelation, everything is so far we are describing in terms of time, right? Can we talk about it in the frequency domain also, right? So so the first thing that is done is that we define what is known as a power spectrum. Okay, we realize that this R has now, after you have taken the autocorrelation function, it has now become a function of tau. So if it is a function of tau, we can always take its Fourier transform. Any function ft under certain regularity conditions, under the regularity conditions that this integral will actually converge, it will have a varied Fourier transform. So now the question is that what will happen if we define a Fourier transform of an autocorrelation function? That function is given the name of power spectrum. Why, we'll see. Why this particular name power spectrum? So at this point of time, power spectrum is nothing but the Fourier transform of autocorrelation for an LTI system, correct? And obviously, if you have a Fourier transform, you can always have an inverse Fourier transform, right? So given the power spectrum, you can also get back the autocorrelation function with this integral. This is just Fourier and inverse Fourier, and incidentally, there are these two are defined generally in all books in the same manner except for this factor. Sometimes people define it here, that is overall you have to have a 1 by 2 pi factor. Sometimes some people put 1 by root 2 pi here and 1 by root 2 pi here and all that. That's just a matter of adjusting the factor. So sometimes you may have a slightly different definition of Fourier transform. We'll work with this. This is more common. So now you have, for example, similarly, so here you have defined this is a general. Now the question is that this autocorrelation function, this correlation function is between what and what. So you can define again between x and x, y and y, x and y, various kinds, and so you will get the autocorrelation. I mean cross power spectrums, auto power spectrums, etc. Various kinds of things. So you can define this Sxy omega. So if you are defining a cross power spectrum, then you take Rx by tau. Now it is reasonably easy to find out that Sxy omega is S star Yx omega. That is, incidentally, if this S omega is a function of omega, what sort of function? Real, complex? It will be a real function of omega. Why? See, inside we are having a complex integral. Fourier transforms are always give us I mean out of real things we get complex things, right? Xt is a real function, but xj omega will be complex. But here we are going to get a real function. Why? Because of the fact that this r tau is symmetric. So r tau will be equal to r of minus tau. So if you are integrating between x and x plus dx on the right hand side, positive side, take the integral on minus x and minus x minus dx. R tau is going to be the same. Now we add them. So r tau is going to be the same, but these two terms will now give you two complex conjugate quantities. So if you remember, do you understand what I am saying? Suppose r tau is a function like this. Now what are you doing? You are actually taking this and then multiplying this one by e to the power j omega tau, minus j omega tau, and multiplying this one by e to the power j omega tau. This is tau and this is minus tau. So the integral term that you will get here is going to be the complex conjugate of the term that you get here. So if you add them up, because you are integrating from minus infinity to plus infinity, so if you consider such pairs of terms, then those complex, then if you add two complex conjugate quantities, you get a real. So all these pairs will add up and keep on cancelling the imaginary term. So you will get a real integral. That's why S omega is real always. It is not a complex function, right? So that is because of this symmetry. So this is on the other hand, if xt is real, it will be an even function. Even function, definitely even function, because of the fact that e to the power minus j omega tau will be equal to cos omega tau plus j sin omega tau. Now the sin omega tau term will get cancelled. So what will remain is only cos omega tau. So cos omega tau is an even function. Correct? So this is fine. Now but Sxy omega may not be. Sxy omega, it is not guaranteed that it will be real. That may be complex very well, because why?
Tau equal to not equal to r minus 2.
So simply because of that fact, so you are not going to get real parts, imaginary parts will not cancel. And this you can easily find out that Sxy omega is equal to S star Yx omega. Why again? Because of the fact that if you go back to this definition, in case of yx, this will become ryx, and remember that we had said that ryx you will get from rxx. If you then you will have to convolve with hm. If you do xy, you have to convolve with h of minus m. So because of that minus m here you will get a complex conjugate quantity. Just you can try writing these. I mean, writing everything is time consuming, but simply writing the integral will give you that this will become a complex conjugate quantity of this. Now let's come back to that old question, that why is it suddenly called the power spectrum? What has power got to do with it? It is called the power spectrum because, see, what is the power? The power is the expected value of xn square. That is, you take every sample you take, that is generally defined as power. I mean, we are not talking of Vi kind of power. We are talking of generally the power of a signal xt is defined as, especially for a random process, power has a sense of square, isn't it? So if you want to have an expected value of power, then you have to take the expected value of xn square. Now, what is the expected value of xn square? That easily you can find out that it is rxx 0. Just put tau equal to 0 in rxx tau. Then you are doing xt1. See, rxx tau is what? Rxx tau, you are taking the expectation of x at t1 and same x at t1 plus tau. This is equal to rxx tau. So you put tau equal to 0. So you will get expectation of xt1 square, and this holds for any t1. So if you want to get the power of the signal, it is nothing but rxx 0. Now you put rxx 0 in this, that is, here you put tau equal to 0. So rather in the inverse one. So here you put here you put tau equal to 0. So if you put tau equal to 0, this will become 1. So if this becomes 1, then my rxx 0 is nothing but 1 by twice pi minus pi to plus pi sxx omega d omega, which means that this sxx omega function, if you see its area under the curve, then you get the total power, right? So in that sense, the function stands for what? It says how the power is distributed over frequencies. So if you integrate from one frequency to another over the whole range of discrete frequencies minus pi to plus pi, then you get the total power, right? If you want to find out what is the energy of the signal stored between omega and omega plus d omega, that will be sxx omega d omega. This amount of energy is actually stored between the frequencies omega and omega plus d omega, because it's a continuous variable. So you cannot say that what is the power at this frequency, that you cannot say, but you can always say that what is the power between omega and omega plus d omega. So you see that this stands for this, just like the probability density function says what is the probability that it lies between x and x plus dx. Here you are asking what is the of the total energy in the signal, how much of energy lies between 5 hertz and 5.00001 hertz. So it is nothing but a density of power, and this density is now expressed over its spectrum, that is it's a function of frequency. That's why it's called the power spectral density. Okay, so hence the name. It comes from this. Now it's very natural to ask that if I have a signal which will have a certain power spectral density and then give it as input, then what is going to be the power spectral density of the output, right? You will ask that, suppose I am giving a white noise. We have not yet defined what is white noise. We will suppose I am given that the input random process has some power spectral density. Okay, so it has some power spectral density. So what is going to be the power spectral density of the output process? Obviously, I mean, common sense will tell us that if you are sending it through a low pass filter, then the power spectral density will probably be preserved around the low frequency zone, and it will be much more reduced around the high frequency zone, because it's a low pass filter. So the high frequency signals will be attenuated, so their power will be reduced. So you see that the filter characteristic has something to do with the power spectral density of the output. That is, the filter characteristic will actually transform the power spectral density of the output. But why? But how? That is the question. So that is very simple to obtain. These are very beautiful results. So it says that Sxy j omega is h star of j omega into Sxx j omega. That is, this is a cross power spectral density, and finally Syy j omega. Again, all these relationships can be obtained just from that basic convolution integral, right? That is, I'll show you from where. From here. See, Rxym is h of minus m into Rxx of m. So we know that if two quantities are related by their, if two quantities are related by the convolution integral, then if you take the Fourier transform of those two quantities, then it will be a product, that we know. So the Fourier transform of this is going to be the Fourier transform of this multiplied by the Fourier transform of this. So what is the Fourier transform of this? It is Sxy j omega by definition. And what is the Fourier transform of this? It is this by definition. And what is the Fourier transform of h of minus m? It is h star j omega, because of this minus m, right? Not following. You can just put it and then put omega equal to minus omega. See, if you have to take, what is h star j omega? H star j omega is nothing but I mean, in place of e to the power j omega tau, you have to put minus j omega tau. So you have to take the complex conjugate, right? So it will be now h of minus m e to the power minus j omega tau, and then sum of, because it's a discrete thing, so we take sum. So you will take m is equal to minus infinity to plus infinity. Now you put, let minus m be equal to k. Then again you will get k equal to minus infinity to plus infinity hk e to the power, now you will get j, this will be j omega m. So it will be plus j omega k. So it is like, so you see, in place of minus j omega you have put plus j omega. So you can equivalently imagine that in place of minus j omega you have put plus j omega. So you have taken a complex conjugate. So then this will simply become h star j omega, just a complex conjugate. So just manipulation, okay, very simple mathematical manipulations. So that's how you get Sxy j omega is h star, and then Syy j omega by the same formula, it will be now h j omega into Sxy j omega, because now you are transforming the first argument, so it will become h. It will not be h star, because now you don't have h of minus m, you have h of m. So finally, if you multiply this, you will get these two, you multiply together, you get magnitude of h j omega square, and this is, so now you have established a relationship that the power spectrum of the input and the power spectrum of the output are related by this quantity. This is the magnitude of the h j omega function whole square, and this makes sense. Why it makes sense? Because the h j omega function, let us say for a low pass filter, at high frequencies its magnitude is going to be low. Remember, Bode plots of low pass filters, if it's a first order filter, it will come down with 6 dB per octave. If it's a second order, 12 dB per octave. So it comes down as frequency increases. So at high frequencies this magnitude is going to be low, and at low frequencies this magnitude will probably approach 1, or if you have an amplifier it may be even more than 1. So this means that for our low pass filter intuition is satisfied by this formula. So at low pass this is going to have a lot of power, and at high pass it is going to have a less number of amount of power. So we'll stop here today. We are gradually approaching our actual subjects, and in a class or two we will probably land in filters. Actually I have to see a little whether what to cover first. I have not yet fully decided whether to cover principles of estimation first and then come to filters, but probably you are getting a bit impatient and you want to actually deal with voltages and currents or signals. So in that case it may be better to start with filters. I understand that we are dealing with abstract fearsome looking integrals for a bit too long, so maybe I'll get into filters. That I have to decide. So that's all today. Thank you.